A very good
MOC.
afternoon to every, a very good afternoon to everyone over here. A warm welcome to all of you to the International Conference on Artificial Intelligence and Machine Learning Applications. I am overwhelmed to welcome our today's keynote speaker for the conference. With our pleasure, I request Dr. K. Balamurugan, Associate Professor, Department of Electrical and Electronic Engineering, K.S. Rangaswamy College of Technology, introduce our today's keynote speaker.
Good evening to one and all present over here. I feel privileged to introduce about the today's keynote speaker, Professor Ajay Anand. Professor Ajay Anand is currently Associate Professor and Deputy Director of Goergen Institute for Data Science at the University of Rochester. Prior to joining the University of Rochester, Ajay was with Philips Research North America and Carestream Health as a Senior Research Scientist and Technical Project Leader. His research interests include biomedical signal processing, biomedical instrumentation, and healthcare data analytics. His recent research has focused on development of novel real-time acoustic signal processing techniques to monitor the progress of ablative thermal therapies and for automated vascular diagnosis. He is a co-inventor on more than 45 patent applications. He has been an invited speaker at the leading ultrasound conferences, including American Institute of Ultrasound in Medicine. Also, Ajay has received his degree in biomedical engineering from the University of Texas Southwestern Medical Center, Dallas, TX, and MS and PhD degrees in electrical engineering from the University of Washington, Seattle. So thank you for giving this opportunity to introduce about you, sir. We welcome you for our keynote session, sir. Thank you, sir.
Great. Thank you, Dr. Balamurgan. Very glad to be here, and thank you again for the invitation from the organizing committee. So, and thank you to all the attendees for participating here. So, I will just share my screen in just a moment. So please let me know if you can see the screen. Can you see my presentation screen?
Yes, sir.
Okay, very good. Yeah, great. So I think we can get started. So let me put this in presentation mode. Okay, so yeah, so welcome everyone. Thank you again for the invitation, and I'm happy to keep this talk interactive. So if there are any questions, please feel free to post either a question or you can you can just speak up, and happy to take questions as we go. Or if you want to wait till the end, that's fine as well. So the topic for today's talk is, as Dr. Balmurgan mentioned, is signal processing and machine learning technologies for low-cost healthcare applications. And just based on my background, this work actually is a combination of work that was done at Philips Research, at Carestream, as well as here at the University of Rochester, where I'm currently. So specifically in today's talk, we will focus on two main topics, two main projects. The first is the use of acoustic sensing technologies, or using acoustic sensors and applying signal processing techniques along with machine learning in order to quantify and detect changes in blood flow profiles. And I'll talk about specific applications where this is used. And the main clinical goal here is to do non-invasive assessment of the flow profile, which is very important clinically. So we'll talk about two specific applications. We'll talk about bleeding detection. This is of great interest to battlefield applications or in the army, for example. And the other would be detection of high-risk pregnancies. The second application, which is more in the therapeutic realm of ultrasound, is to do real-time non-invasive temperature monitoring or therapy monitoring. And the application for this is in the treatment of tumors, where what we have developed is an ultrasound-based method to measure temperature. So we can do real-time temperature measurement. And the key point, we may wonder what is the key signal processing aspect here. And the key aspect here is how can we detect really small displacements using acoustic signals. So that is where the signal processing methods are important. So in summary, for both of these applications, what I will motivate through this talk is that by applying novel signal processing and combining that with machine learning, we can actually provide a lot of clinical value in terms of non-invasive assessment of physiological parameters, and this can help improve the clinical outcomes. Okay, so before we dive into the specific applications, it is useful to understand how biomedical acoustics works or how ultrasound works. So I have some couple of slides just to provide a background because not everyone may be familiar with ultrasound specifically. So essentially in ultrasound imaging, what happens is you have a transducer or you have a sensor. I'm showing that on the left here. It sends out an acoustic pulse. That pulse travels through the object. In this case, it would be the human body. As it travels, there are reflections at every interface. So as it goes through the tissue, wherever there's a change in the acoustic impedance, you will get a reflection back, or you will get scattering from the tissue scatterers. And then what that results in is a series of echoes that you can receive back. So this is an example of the transmit pulse on the top right. And basically, higher is the reflection, higher is the amplitude of the echo, right? And so on the bottom right, this is your basically signal that is coming from the acoustic sensor. And basically, the higher the amplitude of the echo, the stronger is the reflection from the tissue. So this is where the signal processing aspect comes in. How do you take this received echo and how can you process it to extract clinically relevant information? So typically, what I showed on the previous slide is a 1D approach, so one-dimensional approach. Typically, this is done in 2 dimensions. So let's go through this animation. So you have an acoustic sensor, you have a number of acoustic scatterers. This is what you're trying to image. And once you send the acoustic pulse, you basically get the acoustic reflections back. The yellow here shows the raw acoustic backscatter. And then if you apply like amplitude envelope detection, you can get the sort of the envelope of the echoes, and that's what's shown in blue. This is for the 1D case. Typically in clinical practice today, 2D ultrasound is used a lot. And so that's why you have a array of sensors. You don't have one sensor, but you have an array of sensors. It's still imaging the same object. And basically, it will send the acoustic beam in multiple directions instead of just in one direction. And the received echoes can now be combined and you can present it as an image, right? So this is essentially a very typical ultrasound image. And you can see these two are related. On the left is showing just a cartoon of where the different scatterers are. And then on the right is an image where you're able to nicely pick up the location of those scatterers based on the ultrasound echoes. So this is the very basic representation of an ultrasound image, and this is what clinicians used, presently to do diagnosis quite a bit. So it turns out that with ultrasound, just based on how you process the ultrasound echoes, you can actually create a number of different image types. And all of these that are shown here are used clinically. So on the top left, this is called B mode, which is used to just visualize the anatomy. And so it's typically presented as a grayscale image where the strength of the scatterers or strength of the reflections corresponds to an increase in amplitude, and the brighter the image, the brighter the echoes. So that's why it's referred to as B mode images. The middle panel here is called M mode. This is where you can look at temporal information. So as you can see here, the vertical line is one position in the image, in the B mode image, and the bottom is showing you in real time. It can show you the variation over time of that particular line of sight. On the right is what is called the color flow image or color Doppler. We'll talk more about Doppler in just a moment, but this is where you can see that ultrasound can be used not only to visualize the anatomy, but also to visualize the blood flow in real time. You can take this one step further. So the bottom panel shows you the variation of the flow at a given location within the color flow image. And so as you can imagine, this is a very high frame rate acquisition, and you can actually see the systole and the diastole phase in the ultrasound image itself. Okay, so with that background, I will now turn to describing two specific applications. The first, as I mentioned, would be devoted to how can we quantify the blood flow profiles? How can we look at the flow dynamics within the blood vessel of interest? And as I'll motivate in just a moment, this has a number of applications in different settings. Okay, so this application relies on the use of the Doppler principle. So let's spend just a moment to understand what Doppler is. So essentially, the Doppler effect is something that you may have experienced. It's essentially very analogous to when you hear a siren come by, and let's say there's a vehicle that's proceeding towards you. There's a siren, and the frequency of that siren changes as the car or vehicle is moving towards you and away from you, right? So that is based on the Doppler effect. So in terms of ultrasound, the way this works is you have an ultrasound transducer. It's sending out ultrasound pulse at a certain frequency f. The received signal is experiencing the Doppler shift. So let's say the Doppler shift is fd. If you have the speed of sound in tissue shown as c, the velocity of the blood, and then what's also important is the angle of incidence between the pulse and the ultrasound beam. If you have all of this information, you can compute what the Doppler frequency is. It's basically given by this equation here. Another way to look at the Doppler effect is if you are sending out a pulse with frequency ft, if there's no flow, the received signal would have the same frequency fr, which would be equal to ft. However, if there is flow, and depending on the direction of the flow, the received signal can have a frequency that's higher than the transmitted frequency, or it can have a frequency that's lower than the transmitted frequency. So once you can extract the Doppler shift, so that would essentially be fr minus ft, that in turn, using the Doppler equation, gives you information about the blood flow. So how is this used clinically, right? Basically, it's the picture in the bottom right. What you're seeing here is using this extracted Doppler shift, you can now present it like a spectrogram. Spectrogram is the x-axis is time, the y-axis is frequency, or it can be converted to frequency converted to velocity using this equation. And basically what you're seeing is as a function of time, you're seeing the instantaneous velocity or the distribution of velocities in the image. Also, it's useful to note that the brightness of each pixel here represents, what is the strength of the Doppler signal. So in a way, this is sort of a three-dimensional representation of the Doppler information, right? So x-axis is time, y-axis is velocity, and then the power is shown by the magnitude of the intensity of the pixels. Okay, so let's move specifically into this particular application, where the goal was really to see if ultrasound Doppler can be used in a very automated manner in order to do vascular diagnosis. So what is the clinical motivation? It turns out that a number of very important clinical conditions can be actually detected by Doppler ultrasound. This has applications in cardiovascular imaging, for the detection of trauma, for a number of complications related to pregnancy monitoring, and so on and so forth. However, currently these Doppler exams are done by very experienced professionals. So these are typically done by radiologists in India and many countries, or in countries like US, there are specific professions. They're referred to as ultrasound sonographers. They go through training specifically to learn how to use the ultrasound system and how to make these Doppler measurements. So while these measurements are widely used, they require very experienced professionals and expensive instrumentation. So as you can imagine, these array transducers are quite expensive. Ultrasound systems are expensive. So by having these kinds of constraints in having access to ultrasound Doppler, it becomes quite difficult sometimes to get access to doing these ultrasound scans. So the motivation for this project was, how can we automate the collection of Doppler information? How can we automate the diagnosis using Doppler? And if we do that, then the cost for doing the Doppler exam can be reduced. Not only that, it can become more accessible, right? So you can think of like rural settings or settings in which experienced professionals may not be available. But if you have enough automation in the device, and if the system is able to interpret the information on its own, then we can expand the access to care using these devices. So that essentially was the focus of this project, where we developed smart signal processing algorithms that can automatically analyze the Doppler information. And not only that, we also built some specific sensors. And as I show in this comparison here, these sensors are non-phased. So instead of using an acoustic array, they're using a set of individual sensors, which are all connected together, and they're able to automate the Doppler acquisition. So just to compare the current state of the art with what we were proposing, or we proposed in this project, on the left here, you can see this is a very standard ultrasound transducer. We call that as an ultrasound array. It is made up of hundreds of single ultrasound sensors. And because there are so many sensors, the cost is very high, and it requires a skilled operator in order to interpret the images and make the diagnosis. As compared to that, what we have developed in this project is a very simple ultrasound transducer configuration. As you can see here, there's very much limited or small number of elements. This particular transducer has only 32 elements compared to 256 elements, or sometimes 512 elements that may be needed on the transducer on the left. These elements are put together in a mechanical fixture as shown here. And then using this, you can now get 3D ultrasound data acquisition, right? Because this is a volumetric transducer that is covering the entire 3D volume, and so you can get 3D acquisition. What is important to note is the image quality here won't be as good. So this is not used to create images that can be then interpreted. It is purely to acquire ultrasound Doppler signals and then make an evaluation based on the Doppler signals. Okay, so what are the key signal processing challenges, right? So when you develop a system like this, what do you need to solve from a signal processing standpoint? So it turns out that the reflections that come from blood flow are very small. They are very sensitive. There's not a lot of signal to noise. So what I'm showing here on the top right is the comparison between what is the strength of the ultrasound signal, strength of the signals coming from the blood flow as compared to what are the other sources of noise. Some of the key other sources of noise are the vessel wall. So the blood is flowing within the vessel wall, and the vessel walls create significant backscatter or significant echoes. We refer to that as clutter. And as you can see here, the clutter has a much higher signal strength as compared to the blood flow. So the question is, how can we separate these two, and how can we ensure that when we only analyze the blood flow signal, we are not affected by all the clutter that's coming from the blood vessels? So the approach we use here is time frequency analysis. So if we can separate the signal from blood flow compared to the vessel wall in the frequency domain and as a function of time, then we can do an effective job at separating blood flow from the clutter. Also, we know that arterial blood flow is periodic. So if we can apply some algorithms that extract the periodicity of the blood flow, that can be an effective way to separate the clutter from the blood flow as well. The other is, as I mentioned earlier, there's no person who is looking at the images trying to evaluate where the blood vessel is. Typically in a radiology setting, or when a radiologist looks at these images, they have a complete 2D image, and so they can locate where the vessel is. They can position a cursor at that location, and then they can look at the blood flow at that location as well. But in this particular case, we are solely relying on automated acquisition. So basically, the acoustic sensing and the data acquisition algorithms need to be able to provide 3D vessel localization. So you acquire this 3D volume, And within the volume, you need to be able to locate where the blood vessel is. And also that is where we also develop machine learning classifiers to evaluate the blood flow profile. So this is how the typical acquisition would be. So you have the 3D transducer, it would acquire the 3D data. Within that, you locate where the blood vessel is, you locate the flow profiles. And then once you have located the profiles, you apply the machine learning algorithms to automatically say whether the flow is normal or abnormal. Okay, so now let's talk specifically about clinical applications where this information is very useful. So the first application I'll talk about is automated blood bleeding detection. So this is a project that was sponsored by the US Army. And what they were interested in is, can we have a solution where we can detect bleeding in an automated way in the battlefield? So there's a metric used in evaluating flow profiles, which is called the resistance index. Okay, so this is the blood flow that you see in one of the arteries in the leg. And basically what you're seeing is there's a systolic phase, and then there's a reversal of the flow, and there's a very small forward flow during the diastolic phase. There's a metric that is called resistance index, which basically is given by the equation here. It's basically the difference between the systolic and diastolic flow divided by the systolic flow. So as you can see, the lower the diastolic flow compared to the systolic flow, the higher will be the resistance index. And if there's no diastolic flow towards the end of the cardiac cycle, then the resistance index will be close to 1, right? This is basically what this profile is based on is a reflection of the vascular resistance that the blood vessel experiences when the blood is flowing through it. As compared to this top picture, the bottom picture is showing you an example where the resistance index has reduced. And this is what actually happens in a bleed, because when there's a bleed, the blood vessel is open, there's no resistance stopping the flow, and therefore, the blood just gushes out. What that causes is a reduction in the resistance index. And as you can see here, the resistance index for this particular example is significantly lower than for the normal blood vessel. So the challenge in the signal processing focus in this project was if you can quantify the blood flow profiles, and then if you can automatically estimate the resistance index, then we can estimate, what is the whether there's a bleeding or not. This is another application. This is from a clinical application that's looking at monitoring pregnancies. So what you're looking on the left is basically the blood vessel in the fetus. And what this shows you is in a normal fetus, there is a very low vascular resistance because there's good blood flow. And basically you can see there's a systolic phase and there's a diastolic phase. The diastolic flow continues. The flow doesn't stop in the diastole. And basically this would be an example of a low resistance index. On the other hand, if there's some abnormality, it turns out that the diastolic flow actually reduces. So as you can see here, the resistance index would go up. And the bottom plot is showing example where not only does the resistance index go up, but actually there's a reversal of flow during the diastolic phase. Similarly, you can look at blood vessels that are in the fetus, but also in the mother. And basically, depending on the variation of these flow profiles, you can automatically diagnose whether the blood flow is accurate or not, whether the clinical condition is good or not. Okay, so now let's look at how we can do this in an automated way, right? So I just described to you the sensors that we're going to use. I also described to you how the signal acquisition is going to happen. And this is essentially the workflow for how we can acquire the data and analyze the data in an automated way. So we developed custom data acquisition hardware. The hardware was designed to acquire data from all 32 sensors in real time. So essentially, this would be the layout of how the sensors would acquire the data from the blood vessels. So here you see the illustration of a blood vessel. The acoustic beams are shown here. And essentially, as you can imagine, wherever the acoustic beam intersects the blood vessel, you're going to get a very strong Doppler signal, right? So essentially, for every pixel here, you can actually create a blood flow profile, which is shown on the bottom. Wherever the blood flow intersects the beam, you will have a higher power, so higher intensity. Wherever the blood flow is not present or it's very weakly present, you will have a low intensity. So using this information, now if you can aggregate all of these pixels, all of the data in this volume, you can now create a 3D map of the vessel using this real-time Doppler power. And then you can apply some analysis to evaluate, what is the periodicity of the signal. Once you have localized the vessel, you can now go to those specific pixel locations, and then you can compute the Doppler parameters such as velocity, such as resistance index, in order to determine, is this a clinically normal blood vessel or not. So this is an example of how we developed the data acquisition system. It was completely developed in-house. We have a control software which is done using an FPGA. There's an analog front end. This is where all the transmit receive circuitry happens. We want to acquire data and convert it to baseband. So we have a quadrature demodulator. And we relied on National Instruments LabVIEW and National Instruments data acquisition systems to be able to acquire data from all 64 channels. So we have 32 transducers. Each transducer is giving you in phase and quadrature data. So that's why we have 64 channels. Okay, so now let's get into the signal processing aspect in some more detail. So essentially, in order to do automated blood vessel location, we need to perform Doppler analysis on the acquired data. So essentially, we have 32 transducers. Each transducer is pulsing, repeatedly. At each location, we send a series of pulses. And it turns out that, the way to analyze this is if we do time windowing. So if we convert these signals into small time windows, we can then apply the short time Fourier transform. We can then extract the signal power within a frequency range that tells you whether there's a blood flow here or not. We can then detect periodicity, because once we have the flow profile, we can then compute a Fourier transform and look for periodicity. And then once we have done that, we can render 3D maps exactly as you see on the right here. And we also have directional information. We know in which way the blood flow is flowing based on the direction of the Doppler shift or the frequency shift. And based on that, we can tell whether it's arterial flow or whether it's a venous flow. And based on that, we can localize the blood vessel. These are the underlying equations that relate the received signal with the Doppler shift that is imposed on the transmitted signal. And so we have the complete information we need to extract the frequency information. This is an illustration of how this was done in a laboratory setting. This is the anatomy that we were trying to replicate in the lab. So we actually created a lab version of a umbilical cord. So we had arterial flow. Around that, we had venous flow as well. This is our transducer. As you can see, this is the complete transducer in a mechanical housing. And basically, when we acquired the data across all of these 32 channels or 64 channels from 32 sensors, and we reconstruct the data, you can very nicely see a 3D vessel map. If we probe particular locations within the vessel map, you can look at the venous flow, and you can also look at the arterial flow. And there are some locations where you see the venous and arterial flow as well. Okay, so the question now is, how can we use this in an automated way, right? So this is where the machine learning comes in. The signal processing provides you all the features that you can extract from the Doppler profile. So in this case, using signal processing methods, we extracted the clinical parameters. We extracted a resistance index. There's another parameter related to resistance index. It's called pulsatility index. We also extracted the heart rate. And also you can do a number of time frequency analysis. So you can extract the mean frequency, that basically is what is the weighted mean across a vertical line here. That gives you the mean frequency. You can also extract some image-based features. What is the spectral width, which basically means what is the extent of frequencies in the Doppler spectrum. And as you can imagine, these are all features, right? So this is your feature engineering step in a machine learning classification workflow. And now you can subject this to a machine learning classifier. So in this particular case, we just used a k nearest neighbor classifier. And the goal of the classifier is if you feed in these various parameters, can you automatically classify what type of blood vessel is it? And based on the type of blood vessel, whether it's maternal artery or fetal artery, can you then localize, what is the type of artery? And the reason you can do that is each of these blood vessels in the body, and this is just based on how the physiology is, have very unique characteristics. They have very unique characteristics in how their flow profile is, and therefore we can extract that information using feature engineering as well as machine learning classifiers. So in the clinical study that was conducted in a clinical site actually in India, this project was actually motivated by rural healthcare needs in India. What we were able to show is that we have a very high classification rate. The uterine artery was correctly classified in majority of instances. We were trying to separate, is this a uterine artery versus other arteries? Because the clinical diagnosis is based on the uterine artery. And the other case was, can we localize the umbilical artery and also quantify that in an effective way? So as you can see here, in majority of the cases, we were able to classify the umbilical artery as well. But there are certain instances where the umbilical artery performance was weaker, I would say, than the uterine artery. There are a couple of reasons for that. The umbilical artery is a mobile artery, so it's actually it's normally not in a fixed position. So tracking that in real time can be challenging, and as a result of that, the signal quality for the umbilical artery can be affected as well. So this was the one goal of the classification. The other goal is just to see whether, independent of the machine learning aspect, one of the goals was to see whether we can accurately localize the artery itself, right? Because we are doing this in an automated manner, and so we do not have access to an image. So the way this experiments were conducted is we actually used a clinical ultrasound system. We localized the vessel with that. So that serves as the ground truth. And then we also used our system and compared the results between the two systems. And as you can see, our system does a very good job. In more than 90% of the cases, we were able to effectively localize these two blood vessels of interest. So essentially in this project, what we have shown is that we can take an ultrasound workflow, which is done using standard ultrasound systems. And by applying signal processing and machine learning techniques, we can actually automate that entire process, right? And by doing so, we can reduce the cost. We can make it more accessible to do these exams. And as you can imagine, by doing this level of automation, you hope that relatively less experienced professional can also use these systems to make these diagnoses. Okay, so that essentially was the first project. This is based on a very diagnostic application where we are looking at blood flow evaluation. Now I'll switch gears and I will talk about a very novel application using ultrasound, which is for ultrasound-based temperature estimation. So let's jump into this project now. So I'll set the background for this, which is of course quite different from the previous project. In clinical practice, thermal ablation is used a lot. It's mainly used for the treatment of cancers. And the way these procedures work is either an electrode or sometimes it's non-invasive. Heat is deposited into the body. And essentially what the surgeon or the physician is trying to do is heat the cancerous tissue in an attempt to ablate it, to destroy it. And once the treated zone is ablated, the cancer cells are destroyed, and you hope for an effective treatment. There are a couple of different ways in which the heat can be deposited. One is called high intensity focused ultrasound. So this is again using ultrasound, but it's using ultrasound as a much higher intensity. And basically you can apply very localized heat deposition. So the advantage of using HIFU is that it is non-invasive. It can be done from outside the body using an ultrasound transducer. And if you can focus the energy in a very localized way, you can get temperature rise you can get temperatures in the range of 70 to 90 degrees in a few seconds, and that is enough to ablate the tissue. On the other hand, RF ablation is used to also do tumor ablation. And in this case, it's a little more invasive because you have to apply this electrode. It has to go into the body. It's minimally invasive because they can do it through just a small incision in the skin. And in the location where the electrode is placed, you can have very high temperatures, and that can be used to destroy the tissue. So what is the clinical challenge here? The success of the ablation treatment relies on, you want to make sure you're treating the entire tumor. So some kind of feedback or some kind of imaging or sensing is useful. At the same time, you want to make sure that there's minimal damage to the surrounding tissue, right? So essentially, that's the goal for the treatment. So why do we need novel techniques here? What is not currently optimal in clinical practice? It turns out that based on feedback from clinicians, there is high tumor recurrence rates. So that indicates that even though they're applying these treatments and they're able to do this non-invasively or minimally invasive, the tumors are not destroyed completely, right? So which is not ideal. That's one. And the other is sometimes there's damage to critical structures. So essentially you want to treat only the region where the tumor cells are present. You do not want to ablate the normal cells. And therefore, there is motivation to try to optimize these treatments further. How are these monitoring? How is the feedback done today? It's done very simply using thermocouples. So sometimes there are thermocouples on the tip of these electrodes. So as you can imagine, these thermocouples can provide real-time temperature information. But as you can imagine, these thermocouples are sparse, right? There are only limited temperature sensors that you can apply. Typically, these sensors are applied on the tip of these electrodes. And because there are only limited sensors, you get inadequate feedback. You do not get the temperature distribution across the whole volume. You get it only at specific locations in space. One way to mitigate that, and this is what is done currently today, is using MR imaging. So MR imaging is a very well established clinical imaging modality. It turns out that it can also be used for temperature imaging with a specific echo pulse that you can apply in MR. You can actually do temperature imaging as well. And with that, you can actually get a resolution of 1 to 2 degrees Celsius. So that is very, very effective. However, MR imaging is very expensive. It is very time consuming to do these exams. It is very expensive. The access to MR systems is not very easy. And also it's not a real-time measurement, right? So there's always some time lag between the acquisition and when you can do the measurement, which may not be ideal for these kinds of therapies. Also, probably something that limits the access to care is it's not portable. So in many settings, you do not have access to MR, and therefore, this may not be a feasible method to use. So this is where this project focused on how can we use ultrasound, which is much more accessible. It's real time. It's a low cost modality. It's non-ionizing. So how can we use ultrasound in order to do temperature estimation, right? If we can do a temperature estimation using ultrasound, then it's much more attractive to be able to use for RF ablation monitoring or temperature monitoring in general. So the characteristic ultrasound that we are going to exploit is something called the change in the speed of sound versus temperature. So as you heat the tissue, it turns out that speed of sound changes in the body. And based on the change in the speed of sound, we can actually use that information effectively to measure temperature. So on the right, I'm showing a cartoon, basically an illustration of how we can do this. So just imagine that there are tissue scatterers that are located at positions, as shown here. You're now heating the tissue. So on the left, the blue is the cold, not heated. The red is when the tissue is heated. And as you can see, because the speed of sound has changed, the ultrasound echo is going to travel through the tissue faster, right? Because the speed is increased, so it's going to go through and come back faster. Because it's coming back faster, when you do the calculation, assuming a nominal speed of sound, it's going to appear as though these scatterers actually have moved closer to the transducer, right? Because the measurement is purely done based on the time it takes to go through the body and come back. So based on the change in the speed of sound, you're going to have a change in what we call the travel time, the time it takes for the echo to get to the tissue and back. And based on that, any image that you render is going to show as though these scatterers have actually changed their position. Although physically they haven't changed position, it's purely due to the change of speed of sound, and that's the reason we call it apparent change in the position of the scatterers. What that change is can be calculated using this equation, and just based on if you plug in the different values, you will notice that this change in the echoes is on the order of microseconds, or if you convert it to distance, it's on the order of microns. So the signal processing goal here is how can we effectively and robustly develop algorithms that can be very effective to track these small changes in displacement, right? So I'm showing that schematically here using actual ultrasound echoes. So this blue is the ultrasound trace before heating. There's a spot here where the heating takes place. The red is the spot where you have heated the tissue and then you have done a measurement. If you visually see these, you don't see any change. The echoes look exactly identical, but it helps to overlay them one over the other, and you can start to see that the echo is shifted, right? The blue is shifted with respect to the red. As you increase the heating, as you increase the temperature, you will start to see that the red progressively moves away from the blue. And as I said on the previous slide, because of the heating, the tissue scatterers appear to move closer to the transducer. And as I've told you before, the higher the amplitude, wherever the amplitude is high or wherever you see the echoes, that's the location of those scatterers, right? So as the echoes move towards the left, that means that the speed of sound actually increased in that region. So the signal processing challenge here is how can we effectively track these small echo shifts using signal processing methods? And if we can do that effectively and robustly, we can then invert that for temperature, right? So let's look at the signal processing method that is used here. What we have is we have a localized temperature change. So the body temperature is 37. This is an example where I'm showing for 50 degrees. And basically what you'll see is it's a very non-uniform effect on the ultrasound echo, right? So this is the portion where the heat is applied. But this is always a cumulative change, right? So if a certain region of tissue is heated, the ultrasound pulse has to go through that heated tissue to get through other portions of the tissue. So any location beyond the heated tissue also experiences that echo shift, right? So it's a cumulative effect. So if I apply standard signal processing methods, in this case, we applied a windowed cross correlation. So we break this echo into multiple windows, and then in each window, we are trying to cross correlate the red waveform with the blue. And then we can reconstruct the echo shift profile. It will basically look like this sigmoid, it has a sigmoid-like shape. And basically, this is your raw displacement profile. So, based on the echo shifts, you can extract that and it will have this shape here. We can now, we are not interested in this. We are actually interested in temperature. So we have to get rid of that cumulative effect. We can do that using a simple derivative along depth. And once we apply that, we can extract a profile that looks very similar to temperature. We call that temperature-induced strain. It's called temperature-induced strain because, as you can see, it's almost like the red echoes are kind of a shifted or a compressed version of the blue echoes, right? So that's why we introduced the term temperature-induced strain. The thing to remember, this is not a physical strain or a mechanical strain. This is purely a temperature-induced apparent strain, right? So how can we measure the temperature with respect to the information that we are going from the ultrasound echoes? It turns out that this equation is what relates the temperature shift with the temperature-induced strain. And there's, of course, a tissue-dependent parameter alpha, which is the temperature dependence of sound speed. So for this purpose, we assume that this is independently measured for a given tissue type, and we can use that as part of the algorithm. So we have done a series of experiments, looked at different transducer configurations, different experimental setups. So I'll show you one such that was done in the lab. We have a nichrome wire. So we are trying to mimic a heat source here. So we have a nichrome wire, which is applying heat to the tissue sample. This is our setup. We have an ultrasound data acquisition system. We have ultrasound transducer. We have a number of heating elements. We have a heating wire and a number of thermocouples to be able to validate the method. All this is controlled by a data acquisition system. Typically, we have used LabVIEW for this. And basically, we have a power supply that's generating the heat. So this transducer is essentially a 2D transducer, so we can acquire data in 3 dimensions. And what you're seeing on the right here is a field of view that's very similar to this orientation of this nichrome wire. So you can see this zigzag shape. And these panels here show you the temperature rise. When you go from top to bottom, the time is increasing. So basically you're heating. The first 3 panels are during heating. The last panel is during cooling. So as you can see very nicely, we are able to track the temperature rise, right? So it not only maps the actual temperature rise, it also maps the spatial profile of the temperature rise. It matches the zigzag shape of the heating element very nicely. So these temperature rises are quantified, they are tracked. We can see this is a 2D image of the temperature change. And then during cooling, you can see that, essentially you have diffusion. So the extent over which the heat is shown is also increasing. So through this, we were able to document and demonstrate that, we can effectively track the temperature rise in multiple dimensions. We also had thermocouples in the samples. So using thermocouples, we can compare, quantify, how the temperature rise measured using ultrasound compares with what is measured using thermocouples. So as you can see here, there's a very nice correspondence between the temperature rise measured using thermocouples as compared to the temperature rise measured using ultrasound. And also we can now render in all of this in 3D, right? So this is a 3D illustration of the temperature rise at various time points. And basically, as you can see, the region over which the temperature change is happening is progressively increasing. The heat is diffusing, and therefore there's an increased temperature rise over different areas in the tissue. We were able to quantify objectively or quantitatively what is the difference between the thermocouple profile and the actual measurements using ultrasound. And you can see these are very accurate. They are on the order of 0.1 degrees Celsius with a maximum difference of 0.24 degrees. So through this project, we were able to demonstrate that we can effectively do 3D temperature estimation. We can measure these temperature estimates with high accuracy on the order of less than 1 degree, in many cases on the order of 0.1 degree, and therefore we can use this as an effective temperature estimation modality. This is just a movie showing how the temperature rise evolves over time. This is for an ablation experiment where we have an RF ablation needle. This is the hot spot. This is the heated zone. And this is the ultrasound measurement plane. And basically, you're seeing that in that measurement plane, you can actually look at the temperature rise over time, right? So basically, you can look at the temperature rise as a function of time. Now I want to switch gears, and this would be the sort of the one aspect of temperature estimation in ultrasound, which needs some special approaches. We have looked at this plot before. This was the plot of sound speed versus temperature, and it turns out that the sound speed versus temperature is linear in this range between 40 and 60 degrees. And in this higher temperature range, it's actually nonlinear, or more importantly, it's non-monotonic, right? So as you can see from this plot, it's quite straightforward to measure temperature in this linear range, but not so easy to measure in this range where it's non-monotonic. Not only that, as you increase the temperature and as you increase the temperature of tissue, tissue is like 70% water. It undergoes a lot of changes at higher temperatures, right? There's tissue deformation, there's coagulation and expansion and so forth. And so tracking the motion at the higher temperatures becomes a lot more challenging. So the question was, for ablation, you have to measure at the higher temperature. The clinicians are interested in measuring temperatures on the order of 70, 80 degrees. So how can we do that knowing that we have this limitation in the sound speed versus temperature, right? So what we did is we came up with a hybrid approach. The way the approach works is you do real-time temperature measurements in the low temperature range, and then you combine that with a model, which can be done using machine learning. It also uses a physical model, which is a heat transfer model, to expand the temperature estimation in the ablative temperature range. So I won't go into too much detail about this technique, but at a high level, what we're doing is we are acquiring temperature estimation using the ultrasound system in real time. We can do that in the periphery of the hottest zone. So in that region, we can ensure that the temperature is well behaved. It's in the order of 40 to 50 degrees. So, there's no significant temperature rise. We then combine that with a physical model. So this is a model where we have a multiphysics model. So we used a tool like COMSOL, which allows you to do multiphysics modeling. We input the tissue parameters, and then we can predict what the temperature rises. So the idea here is, as long as you have the accurate temperature parameters or the tissue parameters, we can estimate what the temperature rise accurately is, right? And this is what we are trying to optimize in an iterative manner using this algorithm. So we do the forward simulation. We compare the result with what we have measured using the ultrasound transducer or using the ultrasound measurement. We look at the difference and we use the difference to optimize what the tissue parameters are. And this is where the iterative step comes in, where we are continuously optimizing what the in situ temperature tissue parameters are, such that the predicted temperature rise from the model effectively compares with what the measurement that was done using the ultrasound is, right? And this becomes a kind of an iterative approach, and this is a minimization approach where you're trying to find the optimal set of tissue parameters such that this difference is minimized. So we did a series of experiments to quantify this. So what you're seeing here is the comparison between the modeling and the real-time in situ temperature estimates. We have thermocouples here also to be able to give us the ground truth. And as you can see from these plots, there is good comparison between the model output, what we got from the multiphysics model, as compared to the real-time measurements using the thermocouples. What we also observed is at higher temperatures, you have a temperature dependence of these tissue parameters. So what I'm showing here is the temperature dependence coefficient for some of the tissue parameters. And you can see that, for certain values, they compare really well. And so the takeaway from this slide is that we have to account for the temperature dependence of the tissue parameters as well. When clinicians are doing this, they're interested in what is the thermal dose. So thermal dose can be calculated. They're also interested in what is the extent of the ablation. So what you're seeing here is this is a gross pathology slide where you can see a discoloration of the region where the tissue is heated. And basically the heated portion shows you, the heated portion undergoes a discoloration. And the discoloration is related to, what is the extent of treatment that is applied, right? And we can do the same using the temperature estimates that we obtain from ultrasound. We can compute what's called thermal dose. And there's been a lot of work done prior, research done prior that shows that thermal dose is a good representation of the extent of the ablated region. So using this approach, what we're showing here is a comparison between the output from the ultrasound-based model and the gross pathology. And as you can see, the comparison is quite good. It matches to within a few millimeters the estimation between the gross pathology and the ultrasound model. And also, you observe that it matches in both directions. It's one is the long axis view and the short axis view, and in both dimensions, you have good comparison. You do observe that the ultrasound model, overall has overestimated the length of the lesion compared to the gross pathology. And what we believe this is gross pathology is a very visual representation, right? It's not measuring at a cellular level. So the ultrasound model, the thermal dose is better correlated with what's happening in terms of a cell damage at a cellular level, and therefore it's overestimating as compared to what you see, what you see just visibly in a visual manner. Another aspect of this project, and I won't go into too much detail here, is around what we call motion gating. So as you can imagine, when we are doing these measurements, it is quite important that we do a good job with motion tracking. As you can imagine, the liver, which is a target organ for these ablations, is moving all the time. It's located very close to the diaphragm. So what we developed here is motion tracking algorithms. So I'm showing you the extract from a US patent, which we have on this topic. The way this was done is we are actually gating the motion with the data acquisition, right? So the top right here shows you the respiration waveform. We acquired the ultrasound data at multiple instances along that waveform. And then basically you're gating the ultrasound acquisition with the motion waveform. And the idea is, you try to look for a position in the respiration where the motion is the least. And then if you can do all the data acquisition during that time, it would be the most effective, right? So when we normally breathe, we inhale and then we exhale, and then towards the end of the exhalation, there's actually a transient portion where there's actually this tissue is quasi-stationary. So the goal is if you can use that stationary portion to do the ultrasound acquisition for temperature, then we can do an effective job at compensating for motion. So that was implemented in this technique as well. And basically using this method, we were able to show that motion gating can be effective for ultrasound thermometry. Okay, so as a summary for this project, we were able to develop an ultrasound-based technique for doing real-time ablation monitoring. We were able to compute the thermal dose using that method. We were able to expand the applicability of ultrasound temperature estimation into the ablative temperature range. And then using ultrasound sensor data acquisition, by gating it with the respiration cycle, we can effectively do motion gating because motion compensation is a key part of ultrasound-based thermometry. That effectively wraps up my presentation. So in summary, what I've shown you is novel signal processing and automation techniques can be applied on ultrasound on acoustic sensor data. Based on the two applications that I showed you, this can lead to game-changing medical applications. They have varied applications and wide usage. They can help achieve the low-cost goal of many of these healthcare applications because acoustic sensing in many cases can be more effective, cheaper compared to other present modalities. And by doing this effectively, we can actually roll out or provide screening and diagnostic devices that can be more easily applied in low-cost healthcare settings or low-resource settings where there may be a dearth of experienced personnel, and also it may not be possible to have expensive instrumentation and data acquisition capabilities, right? So in those settings, if we can automate using signal processing methods, using machine learning approaches, we can do an effective job at enhancing the quality of care in these low resource settings. Last but not the least, I would like to acknowledge a number of teams that I collaborated with or I was a part of. This includes the ultrasound groups at Philips Research North America, Philips Research Asia. I actually spent close to 6 months in Bangalore, in the research labs in Bangalore, working on these projects, as well as our research teams in various parts of Philips Ultrasound as well. And I want to leave with this cartoon or this graphic on the bottom. Basically, it shows that ultrasound imaging or acoustic sensing is a very interdisciplinary modality. It relies on technologies from various aspects of engineering. You have embedded software, you have signal image processing, you need good transducer materials, good sensing, also good mechanical design in order to be able to do this in an effective way. We rely on a lot of modeling for acoustics. Also, if you have to get these products through in clinical practice, you have to follow all the regulatory guidelines. And more recently, of course, we are tapping a lot into AI and deep learning methods or machine learning methods. And all of this together helps you provide a modality that's very effective, both clinically and from a cost standpoint as well. Okay, that effectively summarizes my presentation, concludes my presentation. Thank you for your attention and happy to take any questions.
Thank you, Professor, for your wonderful presentation.
Thank you. You're welcome. Yeah.
Any questions?
Participants can unmute their mic and raise the questions.
Sir, I have one question, sir. Sir, does wavelength or relative velocity maybe change in Doppler effect, sir? If yes means why, sir?
Yeah, the Doppler effect, well, the velocity will be changing. The Doppler frequency will be changing based on the blood flow, right? So in the body, the blood vessel has different velocity during systole and diastole. And so we can measure that change using the Doppler effect. And please clarify if there's any, if that's what you were referring to, or were you referring to the specific artery?
Yes, sir. Thank you, sir. Sir, I have another one question, sir. Sir, Doppler effect is symmetric or asymmetric, sir?
Yeah, so depending on the direction of the blood flow, you can either have a positive Doppler frequency change or a negative Doppler frequency change. So let's say you have a certain velocity, and let's say it's plus V, you will have a certain frequency change, which would be, let's say, plus F. But if the velocity is minus V, you would have the corresponding frequency change, the same magnitude of frequency change, but it would be in the negative direction.
Thank you, sir.
Yeah, you're welcome.
Dear participants, if you have any more questions.
Sir, I have a question.
Yeah.
You were talking about working with the acoustic sensor, ultrasound sensors directly. Did you mean like you were working it with the Philips machine? You were able to integrate the sensors in the machine? Or how was that you took care of the hardware part of it, acquiring the image with 32 sensors only?
Yeah, great question, Dr. Janti. Yeah, so so we approached it in two ways. One is, of course, within Philips, we had access to the Philips system, so the Philips ultrasound system. And when we used the Philips ultrasound system, we did not change the sensors. We just used the system as it is. But we were able to tap into the signals that the sensor produces and then analyze that offline. So we would just acquire all of the data from the clinical physical Philips sensor, and then process that offline in tools like MATLAB and so forth. For the 32 element custom sensor that was developed specifically for this project, that was not a Philips sensor. We just acquired sensors from manufacturers who are able to actually if you, there are manufacturers out there to whom you can specify what configuration of sensors you want, and they can actually put it in a mechanical fixture, and based on your design, they can build a sensor for you. So this was designed in that manner. So it's a custom sensor, 32 elements, according to our design specification. And then we were able to, we had an in-house team in hardware integration, who were able to develop the data. We were able to develop the front-end electronics to interface with that sensor. So it was a custom sensor and a completely custom system. Oh, I think you're muted. Sorry.
I was really curious about it because when we work with ultrasound, we really have difficulties like how to integrate it with the machine, because we really find it difficult. Actually, I work with ultrasound images, not with signals, but real difficulty is we are unable to interface with the machines.
Yeah, I totally understand. And actually, there are many projects where we have faced that internally also. And that the challenge is because these are commercial systems. There's a lot of software and very custom software that goes into them. So, understanding the whole software framework and how the sensors integrate to the system, yeah, I can totally understand. It's not trivial. So I share that. I share that as well.
I have another question, Professor. So you were talking about the resistive index.
Yeah.
Does it vary from human to human, or it's? I believe it is a constant, right? The index.
Yeah. Yeah, great question. So we looked at the literature for that, and it turns out that the variation, yes, there is variation from one person to another, but it's in over a relatively smaller range as compared to the difference between normal and abnormal. So there's a range of values for normal, and there's a range of values for abnormal, and clinically it has been shown that there's quite some difference between the normal and the abnormal case. So that's what we were laying on.
Yeah. Thank you, Professor, for your answers.
Sure. Yeah, you're welcome.
Any more questions, participants?
So yeah, actually, I could expand on the resistance index. I just recall. So for example, in normal arteries, in normal patients, let's say the range of values would be quite tight. It would be like 0.58 to 0.62, something like that. And then in the abnormal, because there's a significantly reduced vascular resistance, increased vascular resistance, the RI would go up, and the values would be more like 0.8 to 0.9. So, as you can see, there's significant difference between the normal and abnormal values, and that's what you're exploiting for measurements.
Yes, Professor. Like you cannot have a single value then.
That's right. Yeah, it's a range of values, and you hope that the range is different between normal and abnormal, which is the case with the resistance index. Yeah.
Any more
Thank
questions?
you, sir.
Okay. If there are no questions, I think we can end the session. Thanks a lot, Professor, for your time and your projects. It was really good to see both the projects, the thermometry as well as this one. I was actually thinking that people are working only on MRI, like in countries, advanced countries, and nobody is working on ultrasound. And that's really good to see that there are people who are really working on ultrasound. And I actually used to think that low cost modality has to be done because there are a lot of people who do not have sufficient facility to get imaged.
Exactly.
And I'm really happy to see that you are working on it too. Thank you very much for
Sure.
this session which happened today.
Thank you so much. Yeah, and that's a great point you mentioned, Dr. Janti. This project, the motivation actually came from a number of markets like India and China, where access to healthcare in rural settings may be less. And actually, that's true even in developed countries. There are parts of countries where access to care is not the same throughout. So that was the motivation for developing ultrasound-based solutions. And really, the cost aspect was a big motivator.
Okay, Professor. I think we can close this session for today. Thank you very much for being here with us today for the great talk and the great session. Thanks a lot, Professor.
Great. Thank you so much. Thank you for the invitation, and thank you all for participating. Thank you.
Yeah, we'll close the session, Professor. Thank you.
Thank you. Yeah, have a good day. Yeah, bye-bye.
Thank you, sir, for valuable and informative speech. The session was officially ends.
Okay, thank you so much.